Chapter 28, Magnetic Field Due to Currents. Samples. Samples. A wire of a square lobe of side length A, this is A, carries a current I, this is I, this is current. Show that the magnetic field B at a point on the axis of the lobe and a distance x from its center. Now, this is point B. This is x from the center of this lobe. Is given by blah, blah, blah. Now, let's look at this situation. This is the P is on the central axis, the symmetry axis of this lobe. So by a symmetry reason, we know that the B must along this direction of X connect the P and O. Okay, this is the symmetry reason. Okay, and we can see that this is B is superposition of its four line, current line. Okay, so we only choose to calculate one magnetic field produced by one, then we can use the apply to the other line. Okay. Now let's pick up DA or AD, this current line. We will find the magnetic field produced at point P. So what we do, we say we take the orange of this reference at the center of DA, AD, okay, and then we know that connect to this big O, small o and big O, this is parallel to this line, and this is X, okay, and this is half A, okay, half A, okay. And this R, the distance from O to P is half A squared plus X squared, and so on. Now, let's see. We pick up one very small differential section called a DL. Then dB equal to mu 0 4 pi IDL cross R. This is R from the source to the point R. Okay? We see this R in this rectangular triangle is L squared plus R squared. L changes from here to here, okay? R squared is this is a constant number. This R squared in this rectangular triangle is equal to X squared plus half A squared square root. Okay? And we put R in 3, put R in 3, we get dBA. And let's see the direction. The dBA should, by this DL, is perpendicular to IDL, perpendicular to R. So this one must perpendicular to triangle ADP, because these two lines line on this triangle APD. And we find any of these section, okay, differential section DL on this one. That's magnetic field produced point P in the same direction, perpendicular to triangle ADP, right? Because these two lines are on this plane, okay? So we can do just integration, get the BAD, okay? Okay, and with all this one, we have a sine theta. This is a theta, the angle between IDL and R. And sine theta equal to sine pi minus theta, this angle. And this side, in this rectangular triangle, the sine is R over R, R over R. R in this one, R in this one. So we put everything inside, we get a sine theta. Then we find a dBA along the direction, okay? We do the integration, okay? We put everything from where to where we integrate dA is from half A to positive half A. Then left over is mathematics, okay? Mathematics, okay? We put everything inside. Sine theta with a big R or small r, okay? The integration, put everything inside, we get integration, looks like this one. The integration is from minus half A to half A. This looks like complicated. Actually, it's not. This looks at dx x squared plus a squared 3/2. We can check the integration table, find this answer. This answer is L over L squared plus x squared plus half a square and a square root, and we from minus half a to plus half a, and we get the answer. Now this is the answer, BAD. And we find out the other three lines, current line, here produce also the same magnitude but different direction. Okay, we know that. Okay, because the final B must be along the x direction by symmetry reason. So BAD, wait, total B equal to 1, 2, 3, 4. 4 this parallel to the axis. That's BAD cosine alpha along the x direction. What is cosine alpha? You look at this alpha equal to this alpha. Why not? This line perpendicular to this line, and this line perpendicular to this line. So they are the same. And cosine this alpha equal to half a over big R. And half a, the big R equal to x squared plus half RC. We get this one. All right. Then we get a B. This is the answer. Now, let's look at this answer further. If we stand x, p is far, far away from this one. From physics point of view, we cannot see this as a square or this is wrong. We just know this is a current loop. Okay? And when, look, this x approached infinity, what happened? That means we look at this far, far away. We want to find the b. In this case, we drop this one. We drop this one because they are too small. This is what physics do, okay? And we get this as 4 mu I a squared pi 4x squared and square root 4x squared, okay? And we multiply, we find this is equal to mu 0, 4 and 4 cancel out. This is equal to 2 pi, okay, mu 0. This is mu x cubic. What is mu? Mu equal to IA, is IA squared. Because this is a dipole, magnetic dipole of this loop. Okay, it's IA. Okay, and so we are familiar with this one. We just get this one. This is a magnetic field produced by a magnetic dipole at a far, far away distance. Sample. As shown in the figure, a cycle of radius r with current I2 cycling around, this I2 is this direction, okay, is located on the same plane as a long y with current I1 does. This I1 goes up. The distance from the center of the circle O to the wire is L. Find the force acting on the cycle by the wire, because it has produced magnetic field and you have a current. Okay. In order to find the force acting on the circle, we look at a very small section. Okay, this is a ds. Okay, this is ds is located, okay, r from the wire, and the angle theta to the x-axis. Okay, and it's very tiny. We call this called a d theta, and the length is r d theta. Let me calculate the force acting on it, because this magnetic field now that was equal to IDL cross B. Okay. So DF equal to I2, this is the current, DL, this small section, cross B. That B is B1, produced by this one, I1. And we see, okay, this is ideal direction along tangent. B is perpendicular into the page. So I across B is df, perpendicular to the plane, to the B, perpendicular to the section. So df is along the radius of r. Okay, yeah, and see dl is r d theta, very small section. The B, we know that one equal to mu I1 produce 2 pi r. R the distance, this one to the r. What is r? We make a current perpendicular to this one. This r equal to big L minus this section. And this section equal, in this rectangular triangle is r cosine theta. So r equal to L minus r cosine theta. And then we see, and when you see, we put together. So FB on this line is integration of FB, okay? And FB is I2 dl cross B. It looks like it's very simple, but actually it's not, because this is a vector equation. You cannot do the integration. We have to dissolve into x component and y component, find the FBx, FBy, and then we recombine this component, become a BFB. What we do, by symmetry reason, we say Fy equal to 0. This symmetry, look at, because B are not symmetry relative to this O. Yeah. That's B on this side because R smaller is larger, and this one is smaller. But if you look at this one, okay, upper part and the lower part are symmetry, okay. So finally we find Fy is 0, we only find Fx. What is the Fx? Fx equal to F df cosine theta. Okay? We put a df, we put a cosine theta. Okay? This is a Fd. This is, we have low this one. I dl r theta. Cross B. B is mu 0, I1, 2 pi r. R is L over C. This is df cosine theta. Integration is theta. It's a d theta. Theta is from 0 to 2 pi. From 0 to 2 pi. Okay? Well, that's the answer. That's the answer. Well, this is not easy calculus. Okay? I'm not good at it. And I copy from some book. Okay? And we get this answer. Sorry for that. I'm going to do it. Okay? Physics, I think, explained it, how to do it. Sample. An equilateral triangle ABC with current I2 cycling around. It is located near a very long straight conducting wire, XY, is in XY with current I1. Both are on the same plane, as shown in the figure. One side AB of the triangle is parallel to the wire XY. Find the force acting on the triangle by the conducting wire XY. This is the current I2. Okay? Now, let's see that you have 3 lines in this equal length. Okay? Yeah. We look at this AB. AB, force AB should be perpendicular to B. The B produced by the XY is by the right hand rule, is in perpendicular to the page, into the page. Okay? And I is to B, this one. So I cross B by the right hand rule is this one. So AB line was exert a force F towards the wire, same direction. Okay? Yeah. So the total force equal to I2A. This is a total length, okay, times the B. They are perpendicular. Okay? Yeah. The B is mu 0 I1, this distance is B. Okay, 2 pi RB. That's easy. Now look at this I2. We know I2, this is I. The DF in intersection must perpendicular to the I, perpendicular to the B. So it should be around this direction. All the same direction. Okay? And we find, okay, this one, same thing like BC. It should be perpendicular to BC. Okay, along this direction. And they are symmetry. Symmetry. Symmetry means top part and bottom part are the same, but right part is not same. So what we really have find FBFA. What is F2? Let's look at this one. This is equal to I to B. B is mu 0 I1. This is R. Look, so this is R. Okay, 2 pi R. And then we go to DL. DL. When in integration, we get this DF. Okay, along the air direction. And this is very confusing because DL is along the direction. R is direction. Different section, they are different. So we have to find the relationship between DL and DR. The integration, it should be from B to C. We don't know why, because R is related to air, the location of DR. Different section DR with different R, okay? So anyway, I write it integration from B to C. We rewrite the detail later. DRX, I want to change it. Change DR to DR. That relationship is, this is DL, and this is DX, X direction, DX. So we find a DR. DR equal to DR cosine 30 degree. So we write this one and write it, take everything out without R, and we get the dr of R. This is very easy. The integration is log. Now the limit is from here. Okay, R is from here, B to here, C point. This distance equal to B plus this one. And this one is very easy because this is an equilateral triangle. It's very easy to find this one. Okay, so this is a B at this point is B plus square root 3 A over 2. The length of this triangle is 8. Okay, now this is very easy. We get this to the log, okay, and we put it, so you get the answer. And then finally, the total F equal to, on this one is this one minus these two components, okay. So F equal to F1 plus F2 cosine 60 degree, F3 cosine 60 degree. Finally, we get the answer. Okay. Example. This figure shows a cross-section of a long cylindrical conductor of radius 8, containing a long cylindrical hole of radius B. The axes of the two cylinders are parallel and are distance D apart. A current I is uniformly distributed over the cross-hatched area. There's a hatched area in the figure. Question A. Use the superposition ideas to show that the magnetic field at the center of the hole, this one, is blah blah B. Question B. Can you show that the magnetic field in the hole is uniform? Now, this cylinders, we can look at the solid cylinder minus solid this one. We get this composition. And the current density, I, is the total I over this area, pi A squared, minus this area, pi B squared. This is current density, J8. Let's review the magnetic inside a long straight wire with current we studied before. Okay, remember that? I want to find the magnetic field B at this location R. What we do, we make a Amperian loop. Okay, in this case, we suppose is counterclockwise as a positive direction, and we use the Ampere's law. Okay, and finally, okay, this is a question is the I net inside this Amperian loop. Okay, and this is suppose is the total zero and the ratio of the area. Okay, in this we suppose the current density is constant. Okay, and then we get that mu make it equal. And make it equal, we find B. B equal to mu 0 I of 2 pi r times r over r. Remember, this formula is different from that in textbook. Okay. We use this formula. Now, let's define the magnetic field at point P, which is in the hole. Okay. P is a point in the hole. Okay. We know that. Suppose this is P to OA is distance r. This is the axis of the A. This is axis of the cylinder B, the center. Okay. This is small r. They are all changes with different P. Okay. And we know the magnetic field P is BA minus BB. Okay. The BA is whole solid, big cylinder. BB is a whole solid, small solid cylinder. Okay. Now, we know that one. This is a BA, because BA is where I air cross air. This I air is called this one. I air cross R is this direction. Okay. And so BB from here is I air. This is called I air towards you. R air cross R. So this is BB. Perpendicular this perpendicular to this. Okay? And let's set the reference frame orange at point P. This is X direction, this Y direction. Okay? And so that BA. BA by our calculation is mu 0 2 pi, this radius A, big one. Okay? The I, what is the I? I is the I density multiplied by its area, pi A squared. Okay? So this is the current I, A. And then we know this is a magnetic field on the edge of this cylinder. We have a ratio. The ratio is this R, this is the big one, the small R of A. Let's see BB, the same thing. The difference thing is the current, okay? The current is a small cylinder. So this is current density multiplied by area, pi B squared. And this is the IB. We also have a ratio. This is R over B. Okay? Yeah, this one. And then you see this one, pi A squared is pi A squared cancelled out. This means R. This is a pi B squared, pi B squared cancelled out. So finally, we get B. Okay. Now, before we find B, we sort of really introduce this angle. We call it alpha. This alpha equal to this alpha. Why? Now, this line perpendicular this line. This line perpendicular this line. So they're equal. Another thing, theta is OA, OBP. This angle equal to this angle, BB, and perpendicular dashed line. Why? You know, this dashed line equal to this one. This line perpendicular to this one, so the same. We will use it later. Now, you see the B? BX is BAX minus BBX. BAX is BA sine alpha minus BB. BB X equal to BBX times sine theta. Okay, this is theta. Okay, sine theta. Now, we put this number inside. Look at it. This is a common thing. This is a common thing. Okay, and I have a R. Okay, R sine theta. This is R sine theta. And by. By is BA cosine alpha, and BB cosine theta. And we put inside, we get this number. Okay, we got the R sine cosine alpha, small r cos theta. We take the common factor out. Now this is the answer we get. Now let's see. R sine alpha. This is R sine alpha. This is a dashed line. This line. Small r sine theta is R sine theta is this line. So they cancel out. You can 0. And let's see why. R cosine 1. R cosine theta. What is it? Cosine theta? This one. Okay. And small r cosine theta. This one. We put them together is D. So By equal to mu 0 to A. Pi A squared over B squared I D. This is a constant. So that we prove the magnetic field in the whole is constant. Of course, including the center.